Okay, what if I told you there's a secret map, a map that actually governs the very atoms of arithmetic? We're talking about something that promises to bring perfect order to what seems like a totally chaotic universe of numbers. And get this, the map is so important that finding its key is worth $1 million. And no, this isn't some sci-fi plot. It's a real-life mathematical treasure hunt, and you and I, we're about to follow that map.
And I'm not kidding about the prize. There is literally $1 million just waiting at the Clay Mathematics Institute for whoever can finally crack the Riemann hypothesis. This thing is one of the 7 Millennium Prize problems, basically the 7 toughest, most profound questions in all of math. And the stakes are just incredibly high. Because the answer, it doesn't just solve some dusty old math problem, it unlocks the fundamental architecture of prime numbers themselves.
So how do we even begin to wrap our heads around this $1 million secret? Well, here's our game plan. We're going to start with the chaos of the primes themselves. Then, we'll see how a guy named Euler built a bridge into their world. After that, we'll have to map out a strange new landscape to find the secrets, which will lead us to this so-called line of perfection. Then comes a crazy twist involving quantum physics, and finally, we'll look at what our world would actually look like if this whole thing is proven true.
All right, let's start at the beginning. Prime numbers. 2, 3, 5, 7, 11, and so on. Think of them as the atoms of math. Every single whole number is either a prime itself, or you can build it by multiplying primes together. Simple enough, right? Well, here's the crazy part. Even though they're the basic building blocks of everything, they seem to pop up completely at random. There's just no simple formula that tells you, hey, the next prime is going to be right here.
Now, it's not like we're completely in the dark. Mathematicians have this tool called the prime number theorem, or PNT for short. It kind of gives us the big picture. It tells us that, on average, primes get more spread out the higher up you go. But that's just the average. It's like knowing the average height of a mountain range, but not knowing anything about the individual peaks and valleys. The PNT doesn't tell us about that local jitter, the random seeming hops and skips the primes take. And that is what the Riemann hypothesis is all about. It's not about the average trend. It's about perfectly taming and predicting that chaotic jitter.
So where did the key to this whole mystery come from? Well, we have to go all the way back to the 18th century, to a genius mathematician named Leonhard Euler. He created this incredible tool, a function that would one day become the absolute heart of the Riemann hypothesis. Okay, this is where it gets really cool. Euler's genius was creating a function that has like 2 different faces. On one side, it's a sum that uses every single whole number. But then, and this is the magic part, it's also a product that uses only the prime numbers. It's the same function. This thing, called the zeta function, is basically our Rosetta Stone. It creates a direct bridge between the world of all numbers and the weird, mysterious world of the primes. The takeaway? If you want to understand the primes, you have to understand this one function.
But of course, there's a catch. The way Euler first wrote the function, it only works for some numbers. To get to its deepest secrets, and by secrets I mean the places where this function equals 0, we have to go off the map. We have to venture beyond the simple number line we learned in school. A special technique called analytic continuation lets us extend the map into this whole new 2-dimensional world. This is the complex plane. It's a landscape where numbers have not just a real part, but an imaginary part too.
And on this new, expanded map, there's this one specific piece of real estate where all the action is. It's called the critical strip. Think of it as a narrow, vertical band on our map, stretching between the lines for 0 and 1. All the important zeros, the ones that actually control the primes, they're all hiding somewhere inside this one little strip. Okay, so fast forward to 1859. A mathematician named Bernhard Riemann takes Euler's function, he takes this new complex map, and he makes a guess. And it is one of the most breathtakingly simple and powerful guesses in the history of science. He didn't just say, hey, the zeros are somewhere in this strip. No, he claimed to know their exact address. So let's just break this down real quick. The zeta function has 2 different kinds of zeros. First, you've got the trivial zeros. Honestly, they're kind of boring and predictable. We know exactly where they are. But then you have the non-trivial zeros. These are the important ones. The ones that hold the secrets to the primes, and they all live inside that critical strip. Riemann's big idea was about a very, very specific place inside that strip. A perfectly straight, vertical line running right down the middle. A line where the real part of the number is exactly 1/2. This is the famous critical line. And this is it. This is the whole thing. The single, bold claim that has obsessed mathematicians for more than 150 years. The Riemann hypothesis says that every single one of those infinitely many super important, non-trivial zeros lies precisely on that one perfect line, the line where the real part is 1/2. Not close to it, not kind of clustered around it, perfectly, infinitely, on it. If he's right, it means the chaos of the primes isn't real. It's just an illusion, hiding a deep and perfect order underneath.
For over 100 years, this was just a problem for pure math nerds, right? Just numbers and functions. But then, the most powerful clue, the most shocking piece of evidence, came from somewhere completely unexpected. It came from the world of quantum physics.
I mean, first off, the sheer amount of data we have is just staggering. Mathematicians have used supercomputers to check the first, wait for it, 10 trillion non-trivial zeros. 10 trillion. And every single one they've checked lands perfectly on that critical line. But here's the thing about math. 10 trillion examples isn't a proof. A proof has to be for all of them. So the real shock, the real game changer, came from a totally different direction.
This is, hands down, the most mind-bending part of the story. In the 1970s, a mathematician named Hugh Montgomery wasn't looking at the zeros themselves, but at the gaps between them. He came up with a formula for their spacing, and one day, he's showing it to the famous physicist Freeman Dyson, and Dyson just stops. He recognizes it instantly. It was the exact same math, the exact same pattern that physicists use to describe how energy levels are spaced out inside the nucleus of a heavy atom. This is the heart of a field called quantum chaos.
I mean, just let that sink in for a second. The mathematical rule for the spacing of prime numbers, these abstract things that just exist in our minds, is apparently the same exact rule that governs the energy levels inside real physical atoms in our universe. This is not a coincidence. This is a massive clue that pure math and physical reality are connected in a way we just do not understand.
So what's the big deal? What happens the day someone actually proves it? What does a world ruled by the Riemann hypothesis even look like?
Well, a proof would basically change everything, and its impact would ripple out in three huge ways. First, for the mathematicians, it would finally tame the primes. Their chaos would become predictable. We'd have the tightest possible leash on them. Second, for you and me, it would lock down the mathematical foundations of all the cryptography that protects our bank accounts, our emails, our entire digital lives. And third, and this might be the biggest deal of all, it would officially build a bridge between the abstract world of pure numbers and the physical reality of quantum mechanics.
This crazy connection has led scientists to what they call a modern holy grail. They've started to believe that the zeros on that critical line aren't just random mathematical points. They think they're like musical notes being played by some unknown quantum system. In physics, these notes are called eigenvalues. So the big idea, called the Hilbert-Polya conjecture, is that there must be some physical thing out there, some kind of quantum operator, that if you could just find it or build it, would naturally vibrate at frequencies that match the zeros. Finding this Riemann calculator would prove the whole thing instantly.
Which leaves us with one last, absolutely mind-blowing question. This whole thing started as a search for order in the purely abstract world of numbers, but it's led us to the very edge of physical reality itself. So you have to wonder, is the secret law governing the atoms of math also a fundamental law of our universe? The person who finally answers that question, well, they're not just going to win $1 million. They're going to change our understanding of pretty much everything.